Welcome back to The Deep Dive, the show where we slice through complex research and pull out those truly fascinating, actionable insights that help you stay ahead. Today, I want you to join me in imagining a scenario that might sound like science fiction, but is rapidly becoming reality. Picture a vast, remote wilderness, maybe a deep forest, completely off the grid.
Right, no power lines, no easy internet access.
Exactly. But within it, life flourishes, and delicate ecosystems need our protection. Or shift gears, imagine a sprawling industrial plant, miles from human supervision, where massive machinery hums day and night, vital for our infrastructure.
Load.
How do we keep a vigilant eye, or more accurately, a truly discerning ear on these critical, often inaccessible places? How do we detect a rare, crucial event like the faint, unique call of an endangered species that signals its presence?
Or maybe an unusual vibration in a bridge cable that could be an early warning of structural failure.
Right. Without constantly running wires or sending a team out every few days to swap out massive batteries or, being deluged by endless streams of useless data. It's a challenge that, until recently, seemed almost insurmountable, isn't it?
It absolutely is. And this isn't just hypothetical. It's the core dilemma facing the rapidly expanding world of the Internet of Things, or IoT, especially at its furthest edges.
The edge, right.
We're talking about pushing truly intelligent, always-on sensing capabilities right into the environment where the data originates, often in places where power, memory, and the ability to transmit data are incredibly precious, scarce commodities.
Really limited resources.
Exactly. These aren't just about making our homes smarter. They're about fundamental systems for critical safety, environmental conservation, optimizing industrial efficiency, and even national security. The capacity for these devices to discern what's genuinely important at the source without blindly sending everything back to a central hub is not just helpful. It's absolutely crucial for their long-term viability and impact.
Okay, let's unpack this. What if we could imbue these remote devices with the ability to not just listen, but to actually think for themselves, right there, where the sounds happen, using shockingly little power and processing?
That's the key. Yeah.
What if they could autonomously decide in real time that this specific sound warrants attention and only then send a tiny, concise alert? That's what this deep dive is all about. It's a fundamental rethinking of how intelligence operates at the edge. Today, we're diving into some truly groundbreaking research. We're exploring a paper titled In-Filter Computing for Designing Ultralight Acoustic Pattern Recognizers, penned by the innovative minds of Abhishek Ramdas Nair, Shampanu Chakrabarti, and Chetan Singh Thakur. This isn't just an incremental improvement, it's a complete rethink, akin to moving from those bulky vacuum tube computers to sleek, modern microchips, but for the very intelligence of our sensors.
Indeed. We're going to pull back the curtain on their innovative in-filter computing framework. What makes this so profoundly compelling is that it completely revolutionizes how acoustic pattern recognition is actually performed.
How it's done, yeah.
It's custom-tailored for that power-constrained, resource-limited world of smart IoT, where every milliwatt, every bit of memory truly counts. It's about seamlessly building sophisticated intelligence directly into the sensing mechanism itself, making the sensor inherently smart.
Our mission today is crystal clear. We want to understand the ingenious mechanics of how this new architecture works, unravel why it represents such a monumental leap for the future of IoT, and uncover the surprising capabilities it unlocks for a truly connected world.
Right.
By the end of this deep dive, you'll walk away with a clear understanding of how we can make our planet smarter, more responsive, and vastly more energy efficient, even in the most challenging remote locations imaginable. So let's get started on this fascinating journey. So let's really set the stage for why this research is so critical. When we talk about these kinds of intelligent sensors needing to be always on and super efficient, what are some of the typical real-world applications you envision?
Well, you mentioned unattended ground sensors, UGSs. Think border security, maybe? Listening for footsteps or vehicles?
Right, or intruder detection systems in remote facilities, far from any watchful eyes. Or wildlife tracking in vast, pristine natural reserves, trying to monitor endangered species.
Yeah, or even structural health monitoring on massive bridges or critical pipelines that crisscross continents. These are all scenarios where systems operate in isolated, often hard locations, demanding constant vigilance for events that might be infrequent, truly rare, but absolutely critical.
Critical, but rare.
Exactly. The fundamental problem for all these IoT devices is that they must be always active. They need to be perpetually listening, perpetually sensing, tirelessly waiting for that one rare, significant event to occur.
Always on.
Always on. Now, the traditional approach, as you might imagine, involves collecting vast amounts of raw data, be it
Hmm.
audio recordings, vibration data, temperature readings, whatever the sensor is designed to capture.
Grab everything.
Pretty much. Then this raw, unprocessed data is transmitted wirelessly, often via cellular or satellite networks, back to a central server or cloud for analysis. But this method, while conceptually straightforward, is fundamentally unsustainable for remote IoT.
Why is that?
Well, the sheer power consumption required for data storage on the device, for crunching through all that raw data, and especially for transmitting massive amounts of it wirelessly over long distances, it drains batteries at an alarming rate. It severely limits the operational life of these devices, often to mere days or weeks.
So it's not just about the volume of data, it's the enormous energy cost and logistical headache of moving that data. Nobody wants to hike 5 miles through a swamp just to change a sensor battery, right?
Exactly. This is about set it and forget it intelligence. You can't be constantly tending to these things.
Makes sense.
The ultimate goal here, the Holy Grail, is to transmit only alerts, not raw data. Imagine a sensor detecting the distinct call of a rare bird species and sending a tiny encrypted message that simply says, "Alert, bird X detected at these coordinates at this time."
Just the important bit.
Just the important bit. Or identifying an unusual, potentially dangerous vibration pattern in a bridge's structure and sending a critical warning. Anomaly detected in bridge section Z, severity high. This highly selective intelligent transmission is how we can conserve battery power to an unprecedented degree,
Hmm.
dramatically prolonging operational life into months or even years.
Months or years, okay.
This kind of power efficiency is absolutely paramount in these remote, unattended scenarios. It's about minimizing human intervention and maximizing autonomy.
Okay, that makes perfect sense. We want intelligence on the device right at the source. So if we want these sensors to be truly smart, why not just leverage the power of common artificial intelligence techniques like
Right.
deep neural networks or DNNs? They've absolutely revolutionized so many fields, from image recognition to natural language processing. Why can't we just deploy them here on the edge?
This raises an important question. While deep neural networks have indeed achieved incredibly high accuracy and become indispensable in many areas, they confront significant, often insurmountable, limitations when you try to apply them directly to ultralight edge IoT devices for rare event detection. Let's break down why.
Okay.
First, consider the very nature of rare events. By definition, the training data corresponding to these events is sparse. You don't have millions of examples of that specific endangered bird's call or that exact subtle vibration indicating impending failure.
Right, not much data to learn from.
Exactly. And DNNs, particularly deeper architectures, famously struggle to generalize effectively when presented with sparse training data. They thrive on massive datasets to learn intricate patterns, which is often simply unavailable or impractical for rare events.
Okay, so data scarcity is one issue. What else?
Second, even if you could somehow curate enough data to train a DNN for a specific task, the sheer computational resources required for full precision DNN training are simply not available on these constrained IoT hardware platforms.
Tiny processors, limited memory.
Right. And strict power budgets. You might think, okay, let's compress them. You could try to use highly optimized or compressed versions like binary neural networks or BNNs, which use much lower precision numbers.
Like simpler math.
Sort of. But even retraining these compressed BNNs on the IoT platform itself becomes a monumental challenge. Why? Because of the often unpredictable effects of quantization, that process of reducing the precision of the numbers, and also due to subtle, inevitable hardware drift that can occur over time in these low-cost, low-power components. You can't just throw a massive GPU at the problem at the edge.
So retraining on the device is tough too.
Very tough. And there's a third, often overlooked point. While you can successfully quantize the parameters of DNNs, the weights and biases, to save resources and make them smaller,
Okay.
significantly quantizing the input features themselves, the raw data coming from the sensor, often completely obliterates accuracy. Your system effectively goes deaf or blind.
Ah, I see. So the input data needs to stay relatively high quality.
Pretty much. So for all their power, DNNs are ultimately too power hungry, too data demanding, and too rigid in their training requirements for these truly ultralight edge applications.
So if DNNs are out due to their insatiable resource appetite, what about other machine learning methods? What alternatives exist that are better suited for sparse data and the stringent limitations of edge devices?
Well, other machine learning approaches like K-nearest neighbor or KNN and support vector machines, SVMs, have both demonstrated a much better ability to generalize effectively with sparse training data.
Okay, KA and SVMs.
However, among these, SVMs truly stand out for several compelling reasons, particularly for critical unattended deployments. They are inherently more robust to outliers, those unusual, slightly noisy data points that might not perfectly match a clean training example.
That sounds useful for rare events.
It's a major advantage when you're specifically looking for rare, subtle, or anomalous events. Furthermore, and this is a subtle but vital point for on-device adaptation, the mathematical convexity of SVM training ensures that when the device needs to learn or adapt to a new sound, a changing environment, or a new target signature, that learning process is always predictable and stable.
Stable learning, okay.
You won't get wild, uninterpretable results or a system that suddenly forgets what it knew. This inherent stability makes online, on-device retraining truly reliable, which is absolutely critical for devices meant to operate autonomously for years. SVMs also have a long, proven track record as highly effective acoustic classifiers in various demanding applications.
So if SVMs are such a great candidate, robust, good with sparse data, stable for retraining, what's the hang-up? Why aren't all these remote sensors already running optimized SVMs? What's the fundamental gap that even the most efficient traditional SVM implementations couldn't overcome?
That's precisely the question this research tackles. The challenge in existing SVM implementations, even those meticulously optimized for efficiency, is that feature extraction and classification are generally treated as two completely independent processes.
Separate steps.
This separation isn't just a minor inefficiency, it's a fundamental architectural decision that imposes significant overhead both during the initial training phase and during the ongoing inference or classification process on the device.
Can you give an example?
Sure. In a typical SVM acoustic classifier, as you might see conceptually depicted in, say, Figure 2a in the paper, the raw input signal, the electrical signal from a microphone, first goes through a completely separate and often complex feature extraction module.
Like MFCCs or wavelets?
Exactly. Techniques like discrete wavelet transforms, DWTs, or mil-frequency substral coefficients, MFCCs. Its sole job is to crunch that raw data and pull out what it thinks are the most relevant characteristics from the sound wave. Only after this distinct, resource-intensive feature extraction is complete is that pre-processed, high-level feature data then fed into a separate SVM kernel for the actual classification.
Here's where it gets really interesting, because this separation is the Achilles heel for ultralight devices. Treating feature extraction and classification as two distinct sequential steps leads to significant and avoidable resource consumption.
Absolutely. The SVM kernel function itself, particularly a nonlinear kernel, which is often essential for achieving good accuracy in complex real-world sounds, consumes maximum resources. And we know that nonlinear kernels are generally far more demanding than simpler linear ones.
More math, more power.
Pretty much. In older systems, this feature extraction often had to be done offline, using powerful software on a computer, because the actual hardware device couldn't even process raw acoustic signals directly. It needed pre-digested features. That's a massive barrier for true edge intelligence.
So the hardware just couldn't keep up.
That's absolutely right. And it gets worse. Furthermore, these traditional approaches almost always require external memory components for storing the SVM's learned weights, and crucially, its support vectors, the critical data points that define the classification boundary.
Ah, more chips, more power drain.
Exactly. This reliance on external memory, often off-chip, adds to the physical size, power consumption, and overall cost, making them impractical for the incredibly tiny low-power IoT edge devices we're envisioning. They also frequently lack the inherent flexibility to adapt easily to different audio sampling frequencies or to be reprogrammed for new applications without a complete redesign.
So basically, traditional SVMs, while good classifiers, were still too clunky and resource-heavy in their implementation for the extreme edge.
That's the gist of it. They didn't meet the ultralight, always-on, adaptable demands.
So the big problem is that feature extraction and classification have traditionally been like two separate departments that don't talk to each other enough, creating inefficiency and resource bloat. What if we could fundamentally merge them?
That precisely is the core revolutionary insight behind this in-filter computing framework. Instead of separate sequential stages, it ingeniously exploits the inherent computing and nonlinear primitives that are already present within the feature extraction process itself.
Wait, say that again. It uses the computation inside the feature extraction.
Exactly. Think of it like this. Rather than building two separate machines, they realized the first machine was already doing half the work of the second. The goal is to systematically map these crucial linear and nonlinear transformations directly into the kernel functions that are traditionally used in support vector machines.
Ah, so the kernel becomes part of the feature extraction process.
Or vice versa, you could say. This way, classification and feature extraction are not just loosely connected. They are co-optimized from the ground up for both training and inference. They become one seamless, elegant operation.
What's fascinating here is they're essentially saying that the feature extractor isn't just preparing data for the classifier. The feature extraction is the classifier, or at least intimately integrated into its very function.
That's a great way to put it. It's a completely different, much more holistic way of conceptualizing how these intelligent systems are built, especially at the hardware level.
Where do they get this idea?
Well, the approach is deeply motivated by how incredibly efficient biological systems work, specifically neuromorphic cochlea models. Our own inner ear, the cochlea, is an absolutely phenomenal piece of natural engineering.
Our ear, okay.
It's an incredibly sophisticated, computationally efficient, nonlinear, and causal system that processes sound. It inherently performs various linear and nonlinear transformations to dissect auditory signals. This framework essentially mimics that natural intelligence, leveraging those very processing steps and directly integrating them into the SVM kernel.
Instead of having them as separate pre-processing stages.
Exactly. Separate stages that consume extra power and memory. It's nature's blueprint for efficient sound processing brought to silicon.
So they've merged these two previously separate worlds. What does this look like in practice? How do they achieve this deep integration without the traditional SVM constraints?
This profound integration results in what they call a template-based SVM. This is where it really diverges from conventional SVMs. Traditional SVMs have a strict mathematical requirement. They're kernels.
The similarity functions.
Right, the functions that measure similarity between data points. They must possess a property called positive definite. This property is like a mathematical anchor, ensuring that the optimization problem you're solving always has a unique, stable, and predictable answer. It's a fundamental guarantee.
Sounds important.
It is, mathematically. But imagine being an engineer, and that guarantee forces you to use a less-than-ideal tool for your tiny, power-constrained device. This new framework says, what if we could remove that constraint and choose any function we want?
Any function. That sounds powerful.
It is. In the template-based SVM, you're no longer limited to positive definite kernels. This is a game changer because it gives hardware designers and engineers immense flexibility to define arbitrary functions as kernels.
Okay, how does that work? Instead of one function.
Instead of one complex calculation trying to find similarity based on a rigid mathematical kernel, this framework constructs that similarity score from key individual customizable template functions.
P templates.
Right. The traditional kernel, K, X's, Xn, is replaced by a sum of products over these P template functions. Imagine having P specialized detectors, each precisely tuned to a particular aspect of the sound, a specific frequency band, a certain attack or decay characteristic.
Like mini detectors.
Exactly. The overall similarity or classification decision is then a composite, built up from the responses of each of these P-mini detectors. The critical part is that we, the designers, get to define exactly what those P detectors are looking for.
So you control the complexity.
You control the complexity and, crucially, how much memory it needs. The memory footprint is now determined by the user-defined number of template functions, P, which can be kept small and predictable, rather than the often large and variable number of support vectors, S in traditional SVMs, which can be unpredictable.
This is a powerful distinction. It means we get to pick the functions that best suit our specific hardware constraints and the unique patterns of data we're trying to detect, rather than being stuck with mathematically rigid options that might be incredibly inefficient.
Precisely. It's like having a custom toolkit instead of a one-size-fits-all hammer. This flexibility allows for truly hardware-friendly mappings. You can choose functions that are intrinsically efficient to implement in silicon.
Even functions without a simple formula.
Potentially, yes. It even opens the door to using functions that don't necessarily have a simple closed-form mathematical expression, potentially leveraging the inherent, subtle nonlinearity of the physical device itself as part of the kernel. This is a truly innovative way to approach hardware-software co-design.
Making the silicon and the algorithm dance together, that's a powerful shift. Let's distill the superpowers of this approach. What are the key advantages of this in-filter computing framework?
The paper highlights 5 major advantages that collectively make this framework ideal for ultralight, intelligent IoT devices. First, arbitrary kernels. As we just discussed, it uses a template-based SVM architecture that allows any function as a kernel,
Total design freedom.
pretty much. Second, ultralight and efficient. By seamlessly combining feature extraction and the SVM kernel into one cohesive function, the entire system becomes dramatically ultralight and exceptionally computationally efficient. No redundancy.
Okay.
Third, user-defined memory, a critical practical advantage. The memory footprint is entirely user-defined based on hardware constraints, primarily by choosing that optimized number of templates. P, predictable memory usage.
That's huge for small devices.
Absolutely. Fourth, a fast training algorithm. It features a novel, significantly faster training algorithm with vastly reduced memory and computational complexity, crucial for initial setup and, importantly, for on-device adaptation.
Adapting in the field, right.
Exactly. And fifth, scalability without hardware changes. The system boasts impressive scalability through time multiplexing, allowing more complex tasks by processing more filters sequentially on the same hardware.
So what does this all mean? It sounds like they've systematically tackled the biggest hurdles for intelligent edge devices head-on, delivering a truly integrated, astonishingly efficient, and remarkably flexible solution.
That's a fair summary. It addresses the core issues.
Okay, that sounds incredibly promising in theory. But how do these researchers actually engineer this elegant fusion? You mentioned using a neuromorphic cochlea as inspiration. What exactly is that, and why is it so perfectly suited for this?
Right, connecting back to the biology, the biological cochlea, that tiny snail-shaped organ in our inner ear, is phenomenal. It's an incredibly sophisticated, nonlinear and causal system,
Nonlinear and causal.
meaning its output depends only on past and present inputs, and its response isn't just a simple scaling of the input, it does complex transformations. Its inherent ability to robustly process sound, projecting it into higher dimensional spaces where sounds become easier to classify, makes it ideal inspiration.
So it naturally separates sounds.
In a way, yes.
Yeah.
This framework leverages that natural intelligence, specifically a simplified yet powerful model of how the cochlea works. They use a version of the cascade of asymmetric resonators with fast-acting compression, or CARFAC model, focusing on the CAR, basilar membrane function, and inner hair cell, IHC modules.
CR and IHC. Got it. So how does this biological inspiration translate into the actual in-filter process? Can you walk us through the CR-IHC kernel step by step?
Certainly. It functions as a cascade of PCR blocks, specialized filters. Let's break it down. First, you have the CAR block, described by equation 5. An incoming audio sample, XN, feeds into the first CR block.
Like hitting the first string on a digital harp.
That's a good analogy. Each CAR block is like a different string, tuned to a specific frequency range, mimicking our basilar membrane. Because they're cascaded, the output of one filter feeds the next stage, like a wave traveling down the membrane. These are specialized two-pole, two-zero filters with precise coefficients.
Tuned for efficiency.
Right. Next, the output of each CAR filter, BPIN, goes into an IHC block. This inner hair cell block is elegantly simplified as a half-wave rectifier, or HWR function, basically max zero Q.
Only passes positive values.
Exactly. If the input Q is positive, it passes. If negative, it's zeroed out. This mimics how our inner ear cells respond mainly to the peaks, discarding half the information but keeping the crucial bits efficiently. The output here is DPN.
Power-saving nonlinearity.
Precisely. After the IHC block, for each filter, the DPN output goes to a summation stage, equation 8. Here, the output is summed over a window of W input samples, giving a value speed. This aggregates the energy over a short time window.
Building a stable picture for that frequency band.
You got it. Finally, standardization, equations 9 and 10, common in machine learning. This step involves subtracting the mean and dividing by the standard deviation for each filter output across training samples. It normalizes the features.
Puts everything on the same scale.
Right, which is vital for stable learning in the next stage.
Mhm.
This crucial step creates the final kernel function PMB.
What's truly fascinating here is this entire complex process, CRR blocks, rectification, summation, standardization, it's not just pre-processing, it's simultaneously doing the core work of the SVM kernel.
Precisely. The end result is a p-by-1 kernel vector. This vector, combined with the learned weights, QP and bias B from training, directly produces the classification output, EQ4. It completely bypasses a separate feature extraction module.
The features are the kernel, unified.
Exactly. It's a unified system.
You mentioned earlier that this framework boasts a novel fast training algorithm. That's incredibly important. How is this achieved with the template-based SVM, and why is that so critical for adaptive IoT devices?
That's a vital point. Traditional SVM training involves solving a complex quadratic optimization problem. Think of it like a puzzle that gets exponentially harder the more pieces. M, training size, S, support
Hmm.
vectors you add. The computational cost scales roughly as OM2 or OMS.
Too slow for tiny devices.
Prohibitively expensive for IoT. You'd run out of battery or time. However, the template-based SVM dramatically reduces this. By expressing the kernel as an outer product over P templates, the complexity drops to OP plus M.
Q plus M instead of M squared. That's huge.
It's a massive reduction, especially since P, the number of filters, is user-controlled and kept small. This deterministic lower complexity makes sophisticated learning feasible on the edge.
So it's not just ultralight during inference, when it's classifying, but also in training.
Crucially, yes. And this reduced complexity enables online training. Unlike traditional SVMs needing batch processing, the in-filter approach processes features as an input stream. The device can continuously learn and adapt.
Learn on the fly.
Exactly. If a machine's sound changes due to wear, the system adapts. This makes devices truly deployable in dynamic environments without human intervention. They use a growth transform-based approach for this.
That adaptability is key. Okay, this sounds like incredibly specialized hardware to pull off. What kind of chip are we talking about?
You're right, the hardware matters. The team demonstrated this on a C-Link Spartan 7 series Field Programmable Gate Array, or FPGA.
FPGAs. Why are they ideal here?
FPGAs like the Spartan 7 are perfect for edge IoT.
Yeah.
They offer a very low area footprint and exceptionally low power consumption, manufactured on a 28-nanometer node, which helps efficiency.
Low power, small size.
Plus, they're configurable. The in-filter parameters, the weights, can be tuned and reprogrammed in the field for different applications. Huge flexibility. They offer a unique blend of customizability and efficiency.
Building something like this, getting it from math to silicon, isn't just coding, is it? Lots of hardware-specific details must matter.
Absolutely, it's a journey. First, they simulated it in MATLAB using floating-point arithmetic. Standard practice, high precision for verifying the math.
But floating point is power-hungry on chips.
Extremely. So, to hit that ultralight goal, they painstakingly refined it into fixed-point code. This requires careful choices about how many bits you use for each number.
Fixed point, like using integers with an implied decimal?
Sort of, yes.
Yeah.
It's much more efficient. For instance, the CRIHC kernel itself operates with 12-bit fixed-point code. The train weights, QP and bias B, are stored as even smaller 8-bit values.
Only 8 bits for weights.
Wow. And the mean and standard deviation for standardization use 12 bits. This careful surgical choice of bit depth minimizes accuracy loss while drastically reducing hardware resource use. It's a tightrope walk.
Precision versus efficiency. That attention to detail is remarkable. So how do they actually make it so efficient on the FPGA itself? What clever hardware tricks are they using?
Several sophisticated techniques. Firstly, pipelining. This breaks down the processing of each sample into smaller sequential stages, allowing multiple samples to be processed concurrently at different stages, boosting throughput.
Standard hardware speed-up trick.
Right. But the real ingenuity for area reduction is time multiplexing. Instead of duplicating the hardware logic for each of the P filters, they use a single shared hardware block sequentially.
One filter unit does the work for all P filters.
Exactly. You feed each of the P filter coefficient sets through it one after another. This makes the design dramatically smaller in area. The Cara-Dunn signal orchestrates this, ensuring all filters run before the next audio sample. Brilliant silicon saving.
Clever reuse of resources.
And they apply multiple, carefully chosen quantization levels. For example, the summation might initially be 26-bit, then quantized down to 12 bits, then further to 8 bits after standardization. Empirical testing finds the sweet spot to minimize resources without hurting accuracy.
Optimized co-design again.
Absolutely. So the flow is input, xn in a Carl block, using coefficients from FCMM, IHC block rectification, summation ball standardization, using mean SID from SMEM, multiply accumulate, ME, with weights, QP from WM, made bias addition, B from BMM, classified output, tightly integrated.
That's a masterclass in hardware optimization. Give us some numbers. How ultralight is ultralight in concrete terms? Speed, power.
Okay, for a system using a 25 megahertz clock, 16-bit audio at 16 kilohertz, with 30 filters, the numbers are impressive. Speed. Each sample takes about 300 clock cycles, just 12 microseconds through the pipeline.
12 microseconds fast.
And importantly, a new audio sample arrives only every 1,562 clock cycles, or 62.5 microseconds. This creates a significant efficiency buffer, an idle time of about 1,200 clock cycles, or 48 microseconds, before the next sample arrives.
Lots of headroom.
Exactly. For resource utilization on the FPGA 30 filters, only 50 soldered and 17 lookup tables, LUTs, and 2,864 flip-flops, FSFs. That's remarkably low for modern FPGA, truly ultralight.
Tiny footprint and power.
This is the stunner. Power consumption is only 8 milliwatts MLW dynamic power. Breaking it down, logic, LETs registers 2 milliW, control signals 4 milliW, DSP is 1 milliW, clocks 1 milliW.
8 milliwatts, that's incredibly low, like less than a simple LED indicator light sometimes. We're talking devices running on a coin cell for years.
Exactly, that's the game changer. And this efficiency enables scalability and flexibility. That idle buffer, it means you can, say, increase the sampling frequency up to 80 kilohertz without changing the hardware.
Handles faster audio easily.
Or keep 16 kilohertz but increase complexity. You can support up to 120 filters without major latency issues just using that buffer. Each extra filter adds only 2.5% area and 0.23 milliwatt of power. Very efficient scaling.
Wow. Or slow it down.
Right. If power is paramount, reduce the clock frequency way down, maybe to 400 kilohertz, pushing power below 1 millivoltia, or even a few kilohertz for low-frequency signals, like e.g. CG.
Okay, let's unpack this. This means the same hardware, once deployed, isn't locked in. It can be adapted and reprogrammed for vastly different sensing needs just by tweaking software parameters.
Yeah.
Huge adaptability.
Precisely. Future-proofing built in.
So it's elegant, efficient, flexible. But the ultimate question, does it actually work effectively in the real world? How did they test this thing?
The litmus test, right? Yes, it performs. They validated it rigorously on 2 diverse auditory datasets to show its breadth.
Okay, what datasets?
First, the Environmental Sounds Classification, ESC10 dataset. 400 recordings, 10 classes, everyday sounds. Dog bark, rain, baby crying, chainsaw, etc. They used 1-second clips.
Real-world ambient sounds.
Second, the Free Spoken Digit dataset, FSDD. 2,000 recordings, digits 09, 4 speakers, sampled at 8 kilohertz. Here, they used it for speaker identification, figuring out who spoke, not what digit.
So identifying events and identifying individuals shows versatility.
Definitely. The key comparison was with a traditional SVM, using the same CR-IHC filters for pre-processing, but crucially, treating feature extraction as a separate step.
Apples to apples comparison.
Exactly. Looking at Table 3 and IV in the paper, the resource difference is stark. Traditional SVMs consistently needed way more support vectors than the in-filter SVM needed templates. P fixed at 30.
How much more?
Example, classifying the Wheeler speaker in FSDD. Traditional SVM, 5096 MSC operations. In-filter SVM, just 30 MSC operations.
Whoa, 5,000 versus 30, that's over 170 times fewer operations.
Astronomical difference in computation. Now accuracy. The in-filter SVM achieved comparable performance, but with slight reductions for some classes. Maybe a few percentage points dip for clock tick or sneeze in ESC10 or some FSDD classes.
So we're getting almost the same accuracy with drastically fewer resources. That's a powerful trade-off for edge devices, right? Good enough accuracy for massive efficiency gains.
Exactly. That slight accuracy reduction has a couple of reasons. First, the fixed P templates constraint in the in-filter SVM. Traditional SVM could grow more support vectors, potentially capturing finer details, but at huge cost.
The fixed budget limits it slightly.
And second, the in-filter SVM solution is linear after the CAR-IHC function. Traditional SVM could potentially add another layer of nonlinearity in its kernel mapping across filter outputs. But the computational savings are massive and usually worth it.
Pragmatic optimization. Makes sense. But this raises a question. Can you just keep adding more filters, more P, to the in-filter SVM to get perfect accuracy?
This raises an important question. P is tunable, yes, but it's a trade-off. As shown in Figure 7, increasing filters beyond a point gives only marginal accuracy gains, diminishing returns.
But the cost keeps going up.
Right. Increased latency, more hardware resources, area, power. For their experiments, 30 filters hit the sweet spot, good accuracy within tight resource constraints.
Finding the optimal balance for the application.
Precisely. Efficiency, not just raw power.
Right. And these remote sensors aren't in soundproof labs. What about real-world noise? How robust is this system to interference?
Critical point. They tested this by adding white Gaussian noise to the FSDD test signals at different signal-to-noise ratios, SNRs. The framework proved quite robust.
How robust?
Looking at Figure 8, when trained with noise included in the data, it maintained high accuracy even at lower SNRs. Shows the power of comprehensive training.
Training for the expected noise.
Exactly. If trained only on clean data, accuracy dropped below 80% when test SNR fell below 25 dBs. So training with noisy data makes it remarkably resilient for real-world deployment.
That's essential, knowing it can handle environmental interference if you train it right. We spent a lot of time talking about sound environmental noises, spoken digits, but the paper hints at a much broader impact. So what does this all mean for other applications beyond acoustics?
That's the beauty and true versatility. It's not just audio. Its power lies in its reprogrammability. By tuning the CR filter parameters, adjusting frequency ranges, characteristics, it can be configured for a wide array of signal types. It's applicable to any time series data.
Any time series data, like what?
The underlying principles work for sequential data. Table V gives great examples. Vibration signals for industrial predictive maintenance, detecting tiny changes in machinery vibration before failure.
Catching problems early.
EGEC, signal for remote healthcare. Low power, continuous analysis of brainwaves or heart activity from wearables. Early detection of seizures or arrhythmias.
On-body analysis.
Seismic signals for geology or security. Monitoring earthquake activity or detecting ground intrusions. Ultrasound signals, maybe for edge medical imaging analysis. Accelerometer data for activity monitoring. Fall detection.
That's incredibly powerful one core architecture, adaptable to so many different sensor types, a universal smart sensor brain.
Pretty much. This leads to numerous potential applications minimizing human intervention, reducing errors, providing always-on, low-power intelligence.
Like what specific scenarios?
Think wildlife conservation. Tiny sensors detecting specific bird calls, animal sounds, marine mammal vocalizations, tracking rare wildlife without disturbance, monitoring poaching, and you could remotely reprogram them for different species seasonally.
Adapting to research needs.
Remote healthcare. Wearables analyzing ECG ultrasound on device for early disease detection without constant data uploads. Industrial automation, predictive maintenance using vibration, acoustic, temperature data to prevent costly downtime.
Saving millions.
Security systems, robust voice access, intruder detection in remote, off-grid locations on minimal power.
Here's where it gets really interesting. Imagine tiny smart sensors everywhere, embedded, listening, learning, alerting us to crucial events in real time, completely off-grid, running for years. This isn't just technical. It's a step towards a more aware, sustainable, safer world.
It truly is. It's about empowering the things in the IoT with sophisticated, energy-efficient intelligence right at the data source. Faster insights, more effective actions, reduced burden on networks and power.
And the online training is key.
Critically, it means systems can continuously adapt to new environments or changing data, ensuring long-term relevance and effectiveness autonomously.
Today, we've taken a truly deep dive into in-filter computing and template-based SVMs, uncovering a revolutionary approach for ultralight adaptive pattern recognizers for the IoT. We saw how integrating feature extraction and classification inspired by the human cochlea allows for incredible efficiency, low power, and remarkable flexibility on platforms like FPGAs.
This framework represents a monumental leap, overcoming traditional AI limits at the extreme edge. It offers robust classification with sparse data, and crucially, the ability to adapt and retrain on device. Its performance on diverse sounds and broad applicability to time series data highlight its transformative potential.
As you go about your day, think about all the things around you, the hum of your fridge, the rustle of leaves, the clicks of electronics, even imperceptible vibrations. What if these ordinary signals, captured by an ultralight intelligent sensor using this framework, could tell us a story?
Warn us of danger, maybe.
Or help us understand our world in a whole new, energy-efficient way?
Consider how this ability to bring sophisticated, adaptive intelligence to remote, power-constrained environments could fundamentally change our interaction with the physical world, creating a truly responsive, self-aware IoT.
What hidden patterns might we uncover?
What previously undetectable insights might we unlock when every sensor can not just hear, but genuinely understand what it's perceiving, without constantly needing power or bandwidth?
That's certainly something to ponder as we continue to build our connected future.